Experts in the world on permutation patterns, Brian Nakamura, the former organizer of this very important seminar, who will speak about very interesting developments on permutation patterns.
Okay. Well, thank you to the current organizers for inviting me and for the very exaggerated introduction. Very generous introduction. So I'm going to talk about patterns and permutations, which is a pretty active field right now, and in particular using functional certain kinds of functional equations for enumerating in this setting. So just to start off, so the objects of interest are permutations, which I'll look at in one-line notation. So it's some ordering of 1 through n. And I'll start off with a few definitions. So the first is that for k distinct numbers, let's say a1, ak, and I can assume that there are, say, positive integers, but it can be any distinct real numbers. I will define the reduction of these to be the unique length k permutation such that where the smallest term out of A1, AK is relabeled as 1. The second smallest as 2, and so on. So for any k distinct numbers, I can apply this reduction that converts it into a unique permutation. And just an example, the reduction of 3174. In this case, the smallest entry is a 1, so that's a 1. Next smallest is a 3, that becomes a 2. Next smallest is 4, that becomes a 3, and the 7 becomes a 4. Now, another definition. So given a pattern, say tau of length k, and I'll assume this to be a permutation. Let's see. We say that the permutation pi contains this pattern if there exists some length k subsequence such that the reduction is equal to tau. And of course, if permutation pi does not contain a pattern tau, then we say that it avoids the pattern tau. So, as an example, if my permutation that I was considering was, say, 3, 1, 2, 5, 4, this permutation contains, for example, pattern 1, 2, 3. And there's actually a couple occurrences, but one is the 1 here, the 2 here, and say the 4. The 1, 2, and the 5 is also a 1, 2, 3. Contains a 1, 3, 2 as well. Let's say 1, 3, 2. So there's kind of a low term, a high term, and a middle term. Right? And again, the entries do not have to be adjacent. But it avoids, say, 3, 2, 1. So you can't find any 3 terms that are in decreasing order. So, hope this is clear. If not, then the rest of the talk will make no sense. All right. Now, just a bit of notation. I'll define S n of tau to be the number of permutations of length n, avoiding the pattern tau. And so in the area of permutation patterns, that field began with questions regarding, for various patterns, what can you say about this sequence in N? So just a little bit of background. So if I wanted to avoid the pattern, say, 1, 2, this is sort of a, is everyone following me, is everyone awake kind of question. So I can't have any increase in any of the entries, so everything, it must be the decreasing pattern, so the decreasing permutation, so there's only one possible permutation for each such n, for each n. And likewise, if you're looking at the pattern 2, 1, same thing, there has to be an increasing. And I won't discuss it too much, but here, for every n, the sequence enumerating the pattern avoiding permutations are the same, so these are called Wolf equivalent. And so there's some basic equivalences, such as for certain patterns, if you reverse everything, that's an equivalent pattern, and things of that nature. So these are, in a sense, trivially equivalent. Starts to get a little bit more interesting. So this is these are all my length 2 patterns. This is only 2 of them. So length 3 patterns. So this is fairly well known. So the number of permutations avoiding a 1, 2, 3 pattern is actually given by the Catalan numbers. So one of the many things counted by the Catalan numbers. And actually, in this case, any length 3 pattern, that sequence is counted by the Catalan numbers. And I should mention that with sort of trivial equivalences, that you can quickly whittle this down to 2 cases, 1, 2, 3, and 1, 3, 2. And then these turn out to be equivalent as well. In other settings, this won't be the case, that I'll go into later. And so this has been known for a while. Then length 4 begins to get more interesting and much harder. And so here there's 24 different possible patterns, but only 3 actual cases. 1, 3, 2, and unfortunately not in order. But, and so each of the length 4 patterns are equivalent to one of these 3 in terms of the enumerating sequence. So
does each one have 8?
No. Yeah. I think the 1, 2, 3, 4 and the decreasing, I believe, stand by themselves. I might have to double check. So this one is known. This was done by Russell, 1990. So there's a closed form expression for this generating function is known.
And the sequence.
Sequences in Sloan, or OEIS. Yeah.
I don't know if you know off the top of your head, but is it a long, complicated expression, or is it?
The expression would not fit very well here.
Okay. Yes.
I mean, I might be able to.
Real mind is complicated.
Okay.
Computer is different.
Okay.
If you're interested later, I can email you
Okay.
the expression.
Okay.
But let's go to IAS. Yeah.
And the 1, 3, 4, 2. This one's also known. This is by Sona. 1997. And so here also, closed form expression is known, generating functions are known, and such. And then the last one is not a whole lot is known. Right? And so here, there's no closed form expression known. Nothing really about the generating function is known. We don't even know what kind of generating function it has, if it's algebraic, holonomic, anything like that. And so this is sort of the notoriously difficult one that many feel is intractable and such. So,
And to what end we can evaluate it?
yes, so that'll be one of the punchlines of the talk. But I guess up until somewhat recently, the record was known. The values are known for n up to 25.
Is that an OEIS?
Yeah. Yes. Based off the results from this talk, we were able to extend it now to 31. That's about where it ends.
Yeah.
With some help, but yes.
And can I make a comment? The 6 new values are much more interesting, much deeper than either Bonner result or Garrett's result. That are, in comparison, utterly trivial.
So, being that I'm not yet a tenured faculty member, and I'll be on the job market again soon, I will not add any further comments to that remark. But yeah, so this is a pretty computationally difficult sequence. Now, let me jump back over here. And for length 5 and on, really not a whole lot is known. Basically, given that we can't even finish off the length 4 patterns, we really haven't ventured into length 5.
Except for increasing the...
How about
Except for increasing this a little bit. Okay.
Does it get easier if you look at alternating permutations? It's sign 1 plus 1. Change the S to an A.
Yeah, so that I haven't personally looked into too much. I think it does get a little bit easier because you get a lot more structure to work with. But I haven't personally looked at papers on those.
So you don't even know the number of classes for 5?
No. Yeah. So now,
The number of classes can be just computed.
Yeah, currently you know that.
That's not a big deal.
you can compute for each of the non-trivially equivalent patterns. You can compute maybe up to some number. But the issue is that if those sequences match up and they're not trivially equivalent, you don't necessarily know if they're really equivalent or not. Is the issue.
So conjecture, you know it.
Yeah, so there's a few results regarding equivalences that are non-trivial, but for the most part, there's no general classification. So no classification theorems on when patterns are equivalent or not.
You mean accidentally, coincidence, like 1 to 3 equals 1 to 2 in the length 3 case or not? Or something which is no.
Yeah, so I mean, if I gave you a random length 5, a couple length 5 patterns, there's no result that would necessarily let you know, okay, these are equivalent or not. You might know based off of some trivial equivalences, but in general, there's no
algorithm.
theorem.
No, there also exists some non-trivial equivalence, but you don't know all of them.
Yeah,
Yeah, some part.
there's essentially, I think, 1 or 2 non-trivial. But basically, you would have to get lucky that fall under that umbrella. So now, from here, I'm going to consider a slightly more general idea. And so, I'm going to extend this idea, where now instead of just avoiding a pattern, I'm going to ask how many permutations have exactly R copies of a pattern. So this is what I do. Number of permutations, sum, with exactly R copies of the pattern tau. And of course, the R equals 0 case is exactly that. And so in this setting, even less is known. There's been some work done mainly for length 3 patterns. So for length 3 patterns in small r, there's been a number of papers published on finding generating functions for very specific cases and such. But for the most part, until fairly recently, nothing beyond that.
Does Wolf equivalence carry over? Like if two of them are Wolf equivalent and just like the R equals 0, does it carry over for?
The trivial ones do.
Okay.
I believe the theorems break down. So
Okay.
some of the non-trivial equivalence theorems there break down here.
Is it 1, 2, 3, 4, 5 equivalent to 5, 4, 3, 2, 1? That's all.
Yeah,
Yeah.
yeah, so that's considered
that's
trivial.
real because
Yeah.
we got it.
Yeah, so for example here, now the 1, 3, 3 case is not the same as the 1, 3, 2 case.
No.
Right? If R is greater than 0, for example. So the fact that they're equivalent for the 0 case is almost like a happy coincidence that in this very specific case they're equivalent, but structurally they're actually not equivalent.
And can I ask some philosophical question?
Sure.
Does this refinement seems natural? I mean, does it reveal some recurrence relations which involve R?
Yes, so I'm introducing it precisely because I'll use this to
So
I'll use this to get the avoidance. Right, yeah. Okay. Now just as a quick example. So what I mean by this is that 3, 1, 2, 5, 4, this pattern contains, I believe, 2 copies of 1, 2, 3. Namely, the 1, 2, and 5, and the 1, 2, and 4. Okay. And now our goal will be to compute this more general quantity quickly. And for certain fixed patterns and the small r. So I'm going to begin with smaller example that will hopefully provide motivation to more complicated examples. So I'm going to consider just the pattern 1, 2, 3. And I'll just comment that we can equivalently refer to this as, say, ABC. So sometimes letters are used. And there will be about a 5-minute stretch where what I'm doing may not make any sense. And then hopefully, after navigating through those rough waters, then some of the things will begin to make sense. So you might have to bear with me for a few minutes. But for each n, positive integer n, we're going to have variables t, as well as what we may call catalytic variables x1 to xn. And I'm going to develop a weighted sum to get this. So, let's see, like this. And then I'm going to define a weight function for each I in Sn. I'll have the weight of pi be t to the number of ABCs in pi. And then I'm going to toss in some more stuff. And then a product from 1 to n of xi raised to the number of ABs in pi, where the a is exactly equal to the number I. Okay, so for each permutation, I can create this weight based off of these variables. And the general direction I'm going is that to keep track of the number of occurrences of 1, 2, 3 patterns, I'm going to imagine I have a permutation, and then I'm going to insert a new term at the beginning. And so when I do that, I'm concerned with these potential 2, 3s. I'm concerned with 1, 2 patterns that may create a new 1, 2, 3 when I insert things at the beginning. So that's what this variable is, in a sense, keeping track.
Sorry, Adam. A and B are fixed, right? Wait, what do you mean by A equal to? Sorry. Yeah.
So in a sense, these are 1, 2, 3 patterns. 1, 2.
Okay.
So they're the number of 1, 2, 3 patterns and 1, 2 patterns.
Oh, okay.
Or basically, I should maybe say that here specifically, A is equal to I.
Just right.
Okay. From here, I'm going to define a polynomial in these variables that are just the sum of the weights. And the end result is going to be, so note that if I set the x's to 1, then these vanish.
And 1.
They'll become 1. This
One,
yeah. not 0 vanish, they disappear. You only have a t to the number of occurrences. So basically, this sum just becomes a polynomial in t that keeps track of all the, how many permutations have 0 occurrences, 1 occurrence, 2 occurrence, and so on, as coefficients. So that the coefficient of Q to the R in this thing here, and so I set all the x's to 1, and the coefficient of Q to the R will be exactly Sn tau R, the expression I care about. And so this is one of these rare things in math.
Tau is 1 to 3.
Yes, sorry. 1, 2, 3. Yep. So this is one of these rare occasions in math where you take something, make it more complicated, make it even more complicated, and then somehow that helps you simplify things in the end. So you take something simple and make it uglier and uglier, and then somehow this helps us. And so, let me comment. So in a sense, computing this now, this is sort of our new goal, our new objective. And actually, with these very generalized polynomials, we can actually derive functional equations for this Pn. A functional equation. This particular one is originally due to Newman and Zauberger. And for this, we can actually get a reasonably nice functional equation. And even though we created this very, very ugly thing, we can get this fairly nice functional equation. So this is a polynomial in terms of the polynomial in n, and of degree n. This is then, we have n minus 1 here. Basically, the xi term gets yanked out, and then all the terms after the xi, you scale it by t. And this isn't actually very difficult to derive. The idea is that if we have a permutation that begins with the number I, let's say this is of length n. If we cut off the I, you get a smaller permutation, so we cut off the I and reduce it. We have a smaller thing of length n minus 1. And the idea is that if I know the weight of this object, then I can find the weight of this object when I insert the I. Essentially that when I insert the I, everything here that is I just bump up by 1. And when I insert an I here, all the 1, 2 patterns I have here, where the first term is larger than an I, now from a 1, 2, 3 pattern. So that's where these t's come from. And likewise, we get this from when we insert the I,